Welcome to module 7 of database management systems. This is the second part out of total 3 of introduction to SQL. In the last module, we have discussed about the evolution of SQL, the data definition language part of it, and the basic structure of queries. In the current module, we will complete the understanding of the basic query structure, and we will see how common set theoretic operations can be performed in terms of queries. We will familiarize ourselves with the handling of null values and aggregation operation that will be frequently required for forming queries. So, this is a module outline. These are the topics that we will discuss. So, we start with the discussion of some more basic operations in the query. We have already discussed this, that if we do select star from 2 tables, then it results in a Cartesian product. We have seen this result earlier. Now, by itself, as we had said, that by itself the Cartesian product may not really make a lot of you may not be very useful, but suppose we want to answer this kind of a query, that find all names of all instructors who have taught some course, and for those you also write the course ID. So, what we are interested in is the name of the instructor and course ID. So, we put that on the select clause. These are the 2 tables that are required, because the name of the instructor is there in the instructor table relation, and the relationship between which instructor teach which course is in the teachers table. So, in the instructor table we have the name, in the teachers table we have the course ID, and also this relationship as to which course is taught by which teacher. And here we have the relationship between which ID of the instructor has which name. So, what we do is, when we do this Cartesian product, we will get something like this, as we have already seen, but we want to qualify it with a predicate which say that we will, out of all these combination, we will choose only those where the instructor ID equals the teacher's ID. So, if we look at say in the first row, the instructor ID is this, teacher's ID is this, which is ID of the teachers table, they are same. So, which says that this instructor Srinivasan actually teaches the course CS 101. Whereas, if you look into this row, it says that instructor ID is this and teacher's ID is this, and we are really not interested in this combination, because this combination does not convey anything meaningful. So, by the use of this where clause, we will try to choose only those records where these 2 IDs are same, which will tell us that this particular instructor actually teaches that particular course. So, if we do that, then you will find that majority of the records that actually came about in the Cartesian product are eliminated from this result. So, I have struck them out. So, you can currently see in this part, you can see only 4 records, the 3 courses taught by Srinivasan, so and the 1 course taught by you. So, in the output you will have, have this name part, and this course ID part, because you are projecting on these 2. So, this will be the output table which will get generated, and just to remind you, this is the notion of natural join that we had discussed in relational algebra. In this case, we will actually call it a equi-join, because we are using a equality condition after the Cartesian product to join these two relationships. So, this is a very critical operation in many cases in our database query system. This is another extension of this similar example. So, here we have added another predicate in the where clause specifying that instructor dot department name is art. So, which means that this will now give the names of all instructors in the art department only who have taught some course and specify their course ID. So, in different such ways you can manipulate and create queries. It is possible to rename. We have already seen examples. You can rename a relation, you can rename an attribute, and the style is to use as. So, here you can see that in the select query we have said from instructor as T. So, the name of this relation can be treated as T, and we again see that as instructor as S. So, actually what we are doing a join between the same relation instructor and instructor. So, and we are trying to find out all instructors who have higher salary than some instructor in computer science. So, the some instructor in computer science is specified by this condition because department has to be computer science, and the fact that salary is higher. So, as if you treat that though it is actually a join between a product between instructor and instructor, the same relation, but by renaming you treat them as if they are two different tables having name T and S, and then it becomes easier to write this kind of query. So, otherwise it is quite difficult to write this query to find out, because you need to actually create a product of one relation with itself. Keyword as is optional, you can just write instructor and then the name, the new name that you want to give, and that itself will work. Here is another Cartesian product example. Here given a relation which lists a person and his or her supervisor, we want to find out all supervisors, direct or indirect, of that person. So, I will leave this as an exercise to you to think over as to how we can actually compute this query. SQL supports several string operations, and of particular interest are two specific symbols, characters, which allow us doing certain match. Percentage is used to match any substring, and underscore is used to match any particular character, and we use a keyword like to find out different string patterns that can be matched. So, here we want to find the names of all instructors whose name includes the substring DAR, and by writing this. So, you are saying the predicate is formed is name like this. So, what is there is a percentage before, there is a percentage after. So, anywhere DAR will feature in the name, this predicate will turn out to be true. Otherwise, if there is no DAR in the name, the predicate will turn out to be false, and that particular record will not get selected. So, in this way we can using like we can actually do different kinds of string operations as conditions in the where clause or elsewhere. So, now naturally this brings in an issue of what if my string itself has a percentage or an underscore character. So, the rule followed is you will need to escape that with the escape character that you define. This is a style which you have seen in C programming as well. Patterns are certainly case sensitive. So, it depends, it will distinguish between uppercase as well as lowercase, and these are different examples of string matching that you can do, where you can match at the beginning of a string, end of a string, anywhere in the string, specific number of characters in a string, and so on. SQL supports concatenation, conversion of lower to uppercase and vice versa, and different other common string operations. Those are available as functions in SQL and can be used for convenience. Now, let us address a different question. Let us say we have computed a query, and then often we would want that the result be ordered in according to certain order, particularly the value of certain field. If we want the result to be ordered, then SQL allows you to do that by another clause that you add to the query, which is called order by. So, what this will do, we have already seen this query. This will find out the names of all the instructors, and the names will occur in a distinct manner because distinct is specified, but then the output will be in terms ordered by the name, and the ordering can be descending or ascending. By you can control that by specifying whether you want descending or ascending. By default, the ordering is ascending. So, that makes the presentation of the result often very easy, and you can certainly sort on multiple fields as well. So, it can be ordered based on combination of fields. SQL where clause also allows between as a comparison parameter. So, between can specify two values, so that whenever the field value will be between these two given values, the condition will be predicate will be taken to be true, otherwise it is taken to be false. You can compare based on tuple as well. So, in this case you could have written, you could have checked for equality of instructor ID with teacher's ID and department name with the literal biology, but you can compact it by writing a tuple notation as is shown here. So, these are common convenient ways of writing different where clauses. Now, we have specified that SQL does carry duplicates. So, unlike relational algebra, which set theoretically specify that their duplicates should not be there, in SQL there could be duplicate entries in the same relation. So, there is a this is called, when duplicates are allowed in set theory, then such sets where duplicates are allowed are known as multisets. So, there are multiset versions of the SQL queries, or so to say the relational algebra operations. So, you have a selection which can be multiset selection, which means that if there are certain C1 number of copies of a tuple in the relation which satisfy the condition theta, then all of them will feature in the result, and all those copies can be seen simultaneously because it is a multi-set condition. Similar definitions are hold for projection as well as for Cartesian product. So, I will leave it to you to go through the details and convince yourself that these multi-set relations really extend the traditional single set distinct definition of the relational algebra. So, here is an example where there are two multi-set relations, as you can see, particularly this one which has identical duplicate entries. So, using that you can define a Cartesian, you can define a projection of R1 on B, R1 on B, which will certainly give you, you are doing projection on B. So, it will give you A only. So, you will have this result itself will be a multiset because you will get two A's. So, this result will be like A, and then you have R2 with which you are doing the Cartesian product. So, you will have all possible combinations. All these 6 are the result in the SQL, whereas in set theoretically the result should have been only these two tuples. Now, we take a quick look into the common set operations. So, it is possible to do union, intersection, difference kind of operations very easily with SQL queries. So, suppose we want to find all courses that ran in fall 2009 or in spring 2010. So, certainly the first part of the query is simple. This will give you all courses that ran. So, you are taking out the course ID, from section is where the course running information is provided, and you are putting two conditions which say that they actually these courses ran in fall 2009. So, this is the first query. The second query says the courses that ran in spring 2010, and you have an OR condition in the statement of what you are looking for. So, you do a union. Union is another keyword. So, this will simply give you a relation of the course ID attribute as the only attribute which has records from the first as well as the second query. Similarly, you can find out the courses that ran both in fall 2009 and spring 2010 by using intersect, which basically give you the intersection of the result of the first and the second query. You could also do difference, set difference by doing find courses that ran in fall 2009, but not in 2010. So, what will that mean? That will mean that the result of the first query, from the result of the first query, the results of the second query be subtracted, be done a difference from. So, those that had run in the fall 2009 and then was again run in spring 2010 will get removed. So, that is done through the except keyword. So, in this way you can very easily do set operations whenever that is easy to conceive. Obviously, you can write these queries in several other different forms, but this is just to show you how set theoretic operations can be easily written. You can do set operations like this in terms of find salaries of all instructions that are less than a largest salary. So, again we are using renaming to think of the same relation as 2, and then as if from the relation T we are trying to look at relation S and finding out what are the salaries which are smaller than that, and certainly whatever comes in out is the one which is not the largest, because certainly the largest will not satisfy this particular condition, because it will get compared with itself. You can find salaries of all instructors, and then you can find the largest salary. So, this is all salaries which are less than largest, this is all salaries including the largest. So, what happens if you subtract, that is from this, if you subtract this from all salaries, if you remove the salaries that are not largest, naturally what you get is the largest salary. So, this is an interesting way to find the largest salary. We will see later on that there could be several other ways, particularly the use of aggregate function, which make these computations easier to perform. But these are the typical ways to use set theoretic operations. The set operations, so we have seen 3 of them: union, intersect and except. They automatically, these operations are set theoretic. So, each of them automatically eliminate the duplicate, unlike what SQL by default do. SQL by default does what? Allows duplicates, but set operations will eliminate duplicates because they are set operations. So, if you want the SQL type of behavior, if you want the duplicates to be preserved, then you can have a multi-set version of these set operations, which are known as union all, intersect all, except all, like that. And naturally, if you do these operations, then here is the simple formula of the number of tuples that will get computed in different cases. So, you can study and convince yourself that these are the correct numbers. Let us go to the treatment of, we talked about null values, that we said that it is possible that certain records in a relation may have one or more attributes where the value is not known, and to represent that the value is not known, we are putting a placeholder called null. So, let us see what is the consequence of that null value in terms of doing these query operations. So, the null signifies an unknown value. So, if I do 5 plus null, then naturally the result is null. So, what you are saying that I am adding an unknown quantity to 5. So, then what would you say is the result is unknown. So, that is the basic semantics of adding null to a number. So, it is possible to check if particularly a field is null for a record, and that is done by a predicate is null. So, in this particular query we are trying to find all instructors whose salary is null, that is not known. So, this is a predicate. So, for a particular record for which salary is null, this will become true and that will get included in the result. But for all records for which there is some value for the salary, so salary is known, it is not null, those will not get included in the result. So, the basic semantics of null is then combined with the truth values, because we know our basic predicate logic is two valued, true and false, but now you have a third value unknown, that is you may not know the value of a predicate. So, how does it play around with the true and false values? You can reason through that quite easily. If you are comparing with a null in whatever way, then naturally the result is unknown, so it returns a null. If you are doing any connectives, for example, if you are doing OR of null or true, then the result should be true, because in OR we say that if any of the components is true, then the result is true. So, here you do not need to know what is that unknown value, you can say it is true. But if you do OR with false, OR of unknown with false, the second row, OR of unknown with false, if you do this, then naturally this is unknown, because since this is false, the result would be true only if unknown value is true, and the result would be false if the unknown value is false. You do not know what that unknown value is, so you have to say that your result is unknown. So, using that same logic, you could see verify. I would ask you to verify offline. At home, you please verify that all these combinations of true, false with unknown are valid. So, if P is unknown, is as a predicate will evaluate to true if P is not known. Now, we come to the aggregate functions. There are several aggregate functions. They can be used for convenience, and these are the common ones that operate on the multi-set values. Naturally, aggregate functions operate on a particular column. They try to aggregate on a particular column and return a single value. For example, average would be meaning that we are trying to find average of the values of a particular column. So, here is an example. So, we are trying to find the average salary of instructors in computer science department. So, naturally what you output is average salary. So, mind you, this output relation will have one attribute, which is average salary, and since average salary is a single quantity, it will only have one record. And here I have made use of this aggregate function average. So, it says you do average on the attribute salary. And where do you get that attribute from? You get it from the table instructor. And then we are saying that we are not interested to find average of salary of all instructors. We are interested to find the average salary of those instructors who work for computer science. So, you put this where clause. So, this will ensure that you find the average salary of instructors in computer science department. So, in similar way, you can use other aggregate functions, like if you want to know the total number of instructors who teach a course in this semester. So, you first put the where clause. Naturally, where will you find this information? You will find this information in teachers. Teachers is the relation which tells you which instructor is teaching what course. So, that comes in the from. Then you have to specify that teaching a course in spring 2010 semester. So, the where clause specifies that the semester is spring and the year is 2010. So, this will give you all records which show that some instructor is teaching the course in spring 2010 semester. Now, naturally there could be multiple, the same instructor could happen multiple times, because an instructor may be teaching more than one course. So, you make the instructor ID that you have here, you make that distinct, so that you get only those instructors. Every instructor who is teaching one course or more than one course will feature only once in this total list, and then you simply count it, use aggregate function count on that. So, that will tell you how many instructors are teaching some course in spring 2010. Mind you, this here is critical to use this keyword distinct, because unless you use that, then all that you will eventually find out is not the number of instructors who are teaching the course, you will find out the number of courses that are being offered in spring 2010, because there could be the same instructor teaching more than one course. If you just want to count the number of tuples, you can do count on star, because what is star? Star is all the attributes. So, from if you want to find out the number of courses, you just do count star on course. So, this is showing you the computation of average salary of instructors in each department. So, now what you want to do is earlier you tried to find out the average salary in one department. Now, you want that for all the departments, for each department I want. So, my result now is not a single row, it is not a single value, it is a pair where I show the department and the average salary in that department. So, this is what I want, and this is what I have. So, naturally the information comes from instructor, that is from. What I want is a department name and the average salary, and I want to give it a nice name, AVJ salary. So, I have done a rename. So, I get a AVJ salary here. But then what I want is, I do not want an average done over this whole set of fields. I want separate average to be done here, to be done here, to be done on this, to be on this. So, these are basically groupings by the department. As you can see that this particular relation has been sorted according to the department name. So, when I want to apply an aggregate function on certain subgroups of records, I use this particular clause group by and use a name of a field. So, what it does is, if the values in the group by field, in this case department name, are identical, those records are put together, and over those records an average is computed. So, the average that is computed over these records are put in here, average that is computed in terms of these records are put in here. There is only one record, so average that is computed in terms of that is put in here. So, group by is a very useful feature along with the aggregation functions, and it allows you to club information based on certain attribute and then compute the aggregation on some other field. Mind you, you will have to, when you do group by and create the result ID, result table, you will have to make sure that all your result table attributes are used in the group by, which is not an aggregate function. So, here ID is not used. So, this is not a query that SQL would support. You can further refine your result. You are saying that find names and average salary of all departments, this much you have already done. Now, you are qualifying that whose average salary is greater than 42,000. So, of all that we have, for example, if we look in here, for example, in this music department, the average salary is less than 42,000. So, you do not want that in the result. You want only those where the average salary is greater than 42,000, and the way to do that is to add another clause called having. You will say that the average salary is greater than 42,000. So, you are adding another predicate for actually qualifying the aggregated value. Now, the having clause actually applies after along with the group by, because naturally the having relates to the grouping. So, once the grouping has happened, groups have been formed, then the having clause will be evaluated on that. In contrast, where clause also has a predicate, but the where clause is applied before forming the groups. So, this point, this note has to be understood carefully, because if you have a where clause to choose the records, that will first apply, then out of those records chosen, the grouping will happen, and once the grouping has happened, then the aggregate function will evaluate and the having clause will get evaluated, the predicate of having clause will get evaluated. Certainly, if there are null values in terms of aggregates, then there is a question of what will happen. So, the general strategy is that whenever you perform aggregation, then the null values are all ignored. So, if on that field there is no value which is not null, that is, if all values are null, then the result is null, otherwise the result is computed by ignoring the null values. So, these are what you have. Of course, if you count, then if the collection has only null values, the count will return you 0, but all other aggregates will return you simply null. So, to summarize, we had started the basic understanding of the basic query structure in the last module. Now, we have completed that with some more additional operations. We have understood the set theoretic operations, and very importantly, we have familiarized with the treatment of null values and aggregation functions, particularly the group by and having clauses, and how do null values and aggregation interact in terms of an SQL query.